As we discussed earlier, one idea people are exploring is whether LLMs can handle these tasks involving tabular data. The reality is, LLMs are not naturally suited for these tasks. It is worth noting, though, that in some cases when you prompt an LLM to perform a task, it actually just calls popular Python libraries behind the scenes and is executing them for you. That's definitely a helpful shortcut. You don't need to install anything or write code, but it's important to remember the real work is still being done by the Python libraries and not the LLM itself. Given that, let's consider if LLM can do the task itself, and consider the task creating synthetic tabular data. Synthetic data is artificially generated data by AI models to replicate the statistical properties and the patterns of the real-world data. Let's take a look at how you would leverage generative AI tools powered by LLMs to tackle this task. As a first step, you would typically create metadata or use an existing data description file and provide it to the LLM, asking it to create data. In response, the LLM will produce synthetic data, but much of it often lacks any meaningful statistical patterns. For example, if there is a column for transaction amounts and you specify a range between $0 and $1,000, the LLM might generate values uniformly across the range. So if you ask for 100 synthetic transactions, it could produce 10 values between $0 and $100, 10 values between $100 and $200, and so on, without capturing the real-world distribution of the transaction amounts. To address the lack of realistic patterns, you can prompt the LLM to generate data using the most appropriate distribution based on its prior knowledge. For instance, instead of uniformly spreading transaction amounts, the LLM might now choose an exponential distribution, creating many transactions in the $0 to $100 range and then gradually tapering off for higher amounts. This produces data that feels more realistic and mirrors the real-world trends better than a sample uniform distribution. Next, consider a column in your data like account type, which can take one of the 5 possible values. In your business, you might promote certain accounts more heavily, so naturally, more customers sign up for them. In your real data, this could mean that 80% of the customers have 2 promoted account types, while the remaining 3 account types make up just 20% of your customers. The LLM does not automatically know this context, so you need to provide it. You can then instruct it to generate synthetic data where 80% of your accounts are of the first 2 types, and the remaining 20% are distributed among the other 3 uniformly. Then you realize that similar rules probably apply to other columns as well. So you start writing those rules too. Before long, you have ended up creating dozens of such rules. When you have hundreds of columns spread across multiple tables, this quickly balloons into hundreds or even thousands of such rules, becoming a major effort just to generate realistic synthetic data. Which naturally raises another question: where do these rules come from in the first place? The answer is that they are derived from a combination of real data and business knowledge. You may have examined the actual real data, understood the patterns and relationships, and then codified them into context and rules for the LLM. In this case, an LLM at best is acting as your assistant, helping you write the code with all the rules that govern the data generation. Historically, generating synthetic data using rules involved writing rules manually, either directly in a software language or through a user interface-based tool. In that sense, an LLM is essentially a new programming language, one that's much easier and much more natural to use. So, what is the problem? First, none of the challenges that existed with the rule-based synthetic data generation have disappeared. You still need to rely heavily on your understanding of the data or even explore real data sets to define the right generation rules. Moreover, these rules, or in the case of LLM-based approaches, the prompts tied to these rules, must be continuously maintained and updated as your data or requirements evolve. Second, the complexity of this approach can quickly become overwhelming for enterprise-scale datasets. For instance, one of our customers had 45 tables with over 3,400 columns. In such a case, you'd need to write hundreds, if not thousands of rules to generate meaningful synthetic data. And every time your schema changes, whether you add a new column or new table, you would have to revisit, test, and update your prompts accordingly. Third, this approach isn't really using generative AI to create synthetic data. It's using generative AI to replace your programming tool, but with an added layer of complexity. You now also have to verify that this new programming language actually followed your instructions. For example, you ask it to generate data where 80% of your customers have 2 out of the 5 accounts. You need to confirm that it did so correctly. What often happens, though, is that when the output doesn't match the expectation, the blame shifts to the prompt. Maybe the instruction wasn't quite right. And that's where concepts like prompt engineering, retrieval augmented generation come into play, adding yet another layer of complexity to an already challenging process. So in a sense, it did not make you more productive, but added more complexity to an already existing complex workflow, which is learning and maintaining a new set of rules now described as prompts. So how did we do this before LLMs? Let's revisit the more direct and classical approach. As we discussed earlier, you would use a purpose-built software system designed for a specific tabular data task. For synthetic data generation, one example is the Synthetic Data Vault, or SDV, which is a Python library. Using SDV and creating a generative model can be as simple as writing 2 lines of code, fit and sample. The software looks at your real data, automatically learns the patterns, the relationships, and the rules that exist in that data. It builds a generative model and then uses that and generates realistic synthetic data from it. The amount of human effort required is often less than 2 minutes. In many cases, the model itself can be trained automatically within an hour. Now compare that to an LLM-only approach. What previously took 2 minutes can turn into a much longer process. You spend time figuring out how to prompt the model, how to describe the rules, how to preserve relationships in the data, and how to generate synthetic data that is actually realistic and representative of your real dataset. In other words, you replace a specialized tool with a general purpose one and increase the amount of work required. That is what we call negative productivity. Fortunately, there is a way to get the best of both worlds. The key is not to replace the software system with an LLM, but to use the LLM as an interface to the software system. In the next video, we'll walk you through exactly how that looks like.